The next thing I want to say is more than just a comment. Let's look back to our second comment here, where we say that applicability is obviously what we want and stability is what we have to study. So we need to make sure this holds, and then we get invertibility for free. Well, that was just statement A from our new Polski theorem. You could just draw the same kind of diagram for statements B and C, and they would all say the same. They would all say that this here is what we want. We want applicability or Moore-Penrose applicability, or this property without a name down here. And in order to get these, we need stability, or respectively Moore-Penrose-stability, or respectively stable regularizability. And by the way, if we can make sure we get them, then we get invertibility or Moore-Penrose invertibility for free. Okay, so this is the task now. How do we recognize my sequence is stable or Moore-Penrose stable or stably regularizable? And how are these three properties connected one to another? That's the topic. Okay. And one thing that we did successfully already was recognizing stability by looking at the singular values of my sequence AN. So you have to look at the singular values of every operator AN and then let n go. So let's recall what we found out about stability in this respect, and then let's see whether we can do something similar for Moore-Penrose-stability and the other property. And for stability, we found out in section 4.3 that the key is to have a uniform but positive lower bound on all your singular values, at least starting with AN0. So you can draw a line somewhere here, let's say at epsilon, such that no singular values enter this forbidden region here. So they are all bounded away from 0, and thereby the norm of the inverse, which is 1 over the smallest singular value, is bounded from above, so it's bounded away from infinity uniformly over all n, starting with n equal to n0. Okay, this was stability. Now let's talk about Moore-Penrose-stability. Well, we can almost copy what we said for stability, except that we have to change inverses into pseudo-inverses. But that little change here means that we can relax our condition on the singular values a little bit, because for the existence of the pseudo-inverse, it's allowed to have 0 singular values, and also for the norm of the pseudo-inverse, you can just ignore zeros, and the set of singular values, they do not affect this quantity here. So from now on, 0 singular values are allowed, so that now the condition is that your sets of singular values are contained in the set that is the union of the point 0 set and the interval that starts at epsilon and goes to plus infinity. We should probably bring that expression here in the correct context. So there exists a positive little epsilon and a starting index n0, after which this condition should hold. such that for all n greater than or equal to n0, our singular value sets are contained in this union, so they are either bounded away from 0 uniformly by this global constant epsilon, or they are 0. For stability, we have pretty much the same statement, only that now 0 is not allowed. Okay, so that was stability and Moore-Penrose-stability. And now we have to understand stable regularizability. And I'm afraid before we can draw the corresponding diagram over here, we need a little computation. Okay, so let's do that little computation first. Well, at first we should recall the definition of stable regularizability. Where was it? Many slides ago. One more. Here we go. So it says that there exists an epsilon greater than 0 such that the difference of the epsilon TSVD regularized AN and the unregularized AN goes to 0 in the operator norm. As n goes to infinity, epsilon is fixed. Existence of such an epsilon is part of the definition. Okay, so let's write that down and let's try to understand what this means for the singular values of an as n goes to infinity. Here we are. Okay, so this regularized operator is defined in terms of singular values. We need a diagram of singular values, so I guess we should draw singular values. Okay, well, at first, the singular values of an could be all over the place. We have no idea where they are. I mean, this is exactly the condition that we're trying to find out from this property here. So then we apply the TSVD with parameter epsilon. And we know what the TSVD is doing. It takes the singular values that are between 0 and epsilon and moves them all into 0 down here, and it keeps the rest. So now let's try to compute the difference of these two operators. Well, they have almost the same singular value decomposition, only that the sigma term for an epsilon has the singular values of an epsilon on the diagonal, and the sigma term of an has the singular values of an on the diagonal. But the U matrices are the same and the V star matrices are the same, so it's easy to simplify this difference here. And that's already your singular value decomposition for this difference of the two operators. So here's U, here's V star, and here's your diagonal matrix, and it's the difference of these two diagonal matrices where a lot of cancellation happens, because the singular values that are behind epsilon are in both of these matrices and they will just cancel. So the only ones that remain are the ones that are in an but not anymore in an epsilon. And hence the norm of your operator is the largest of these singular values that didn't cancel. So this norm here is the largest singular value of an that was moved into 0 via the TSVD. So it's the largest singular value of an that's in the interval from 0 to epsilon. Okay, I think we have what we need to draw our diagram here. Okay, so here we have the same axis for the singular values of an0, an0 plus 1, and then some other an with n bigger than that. And let me move epsilon a little bit further to the right, because a lot of stuff's going to go on between 0 and epsilon. So it's perfectly okay to have singular values up here, just like before. There's nothing wrong with that. Okay, and now here comes the condition. The largest singular value inside of this interval has to go to 0 as we go down here. So there is a sequence here, 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 and so on, and that is going to 0, where for the singular values it's okay to be in here, and it's okay to be up here, but not in between. So writing down this corresponding condition is a little more difficult this time, but I'm sure we will get this done. So there exists our epsilon, and of course a starting index n0, and this sequence of upper limits for the green regions that goes to 0, such that for all n after our starting index, the singular values of an are contained in either the green interval or the blue interval. Okay, and that's your condition. So we even have some room down here that we do not need, and that's our table. This here is actually sometimes called the splitting property, because your singular values have to split into this green group that is pushed into 0 by the upper bound Cn that goes to 0, and the blue group that is staying away from 0, well separated by this global uniform bound epsilon. So we can clearly see that stability is the most ambitious one of the three properties. Moore-Penrose-stability is already a bit more relaxed. Now you allow zeros. And stable regularizability is the most relaxed of the three. Here you even allow a green group of singular values that slowly but surely moves into 0, and the others have to stay away. So let's close this little discussion and comparison of the three properties by showing a diagram how these three properties are related to one another. So let's say here is the set of all stable operator sequences. Then a little bit larger is the set of all Moore-Penrose stable sequences. And even larger is the set of all sequences that are stably regularizable. And remember, by our new Polski theorem, part A, for stable sequences we have that A is invertible and the inverses of an converge to the inverse of A. For Moore-Penrose stable sequences, by part B, we have the same with Moore-Penrose pseudo-inverses. And for these stably regularizable sequences, we have to TSVD regularize first before we get them in this Moore-Penrose stable situation, which is why you call them stably regularizable. You can regularize them to turn them into a stable, actually Moore-Penrose-stable sequence. And the little epsilon down here is just the epsilon that we use to bound our singular values uniformly away from 0 here. Okay, let's convince ourselves that actually the three classes are not equal. So we should find examples that are blue and not red, and we should find examples that are black and not blue, and probably some that are red. And maybe we can even find a sequence that's so bad even the new Polski theorem can do nothing to save this method. And let's try to keep our examples as simple as possible. Let's say just diagonal matrices, so that the diagonal entries are their singular values, and we can just verify that yes, they have the desired patterns. So AN could just be this n by n identity matrix. All the singular values are equal to 1, so none of them is 0. Everything is staying away nicely from 0, uniformly bounded from below by some epsilon, let's say 0.9 also. Okay, that's clearly a stable sequence. Okay, now let's look for something that is Moore-Penrose stable but not stable. So let's just put one singular value to 0 and all the rest to 1. So this is now no longer stable because there's a 0 in here, but Moore-Penrose is fine with zeros. Now if you put 1 over n here instead of 0, then you're no longer Moore-Penrose stable, because the Moore-Penrose pseudo-inverse has norm 1 over this, which is n, and that grows to infinity. But if you regularize it, then eventually that will be less than epsilon and thereby turned into 0 by the TSVD, and then you're down to this case, which then strongly converges. Or you could say it like this. I mean, this 1 over n is in this green bit here, which goes to 0, so it's inside an interval from 0 to Cn, which you could take 1 over n itself, and therefore you're in the regime of stable, regularizable sequences. N by n is missing here. Okay, if you want a sequence that's not even stably regularizable, then how about that? Now your singular values get splattered all over the interval 0 to 1, and there is just no splitting in a group that goes to 0 and another group that stays away from 0. No, you just get denser and denser, and you cluster the whole interval from 0 to 1. So this is clearly not even stably regularizable, so you cannot do anything about this by our new Polski theorem. Okay, so this diagram should give you an impression of how bad it can be, and you can still rescue the situation, and the theorem tells you how to do that. But there are also cases there where you cannot help anymore. Okay, I guess that concludes this section, and that concludes chapter 4.